Swayam Prabha. Digital India. Educated India.
Hello everyone. So, we will start now a new module which is rotor spinning. In last module which we have completed, that was the ring spinning. Now, this is an open end rotor spinning. Here we will discuss the twist insertion and the yarn formation. Okay. Now, first basic understanding of twist insertion and yarn formation we will discuss. So, here this is the schematic diagram of open end rotor spinning, where this is a feed roller, okay, and the sliver. Here the raw material is fed in the form of sliver. Sliver is fed to the feed roller, and feed plate and feed roller, that feed plate and feed roller is there, and here from feed roller material goes to opening roller, which rotates at very high speed and which opens the fiber. Now, the opening roller rotates much faster than the feed roller speed. So, that results the complete individualization of fibers. Fibers in the sliver are opened by sawtoothed pin in the feed roller and separated further. A high draft ratio is there. So, it is actually at a very high draft ratio, it separates the fiber to an individual stage. Okay. So, at this opening roller, fibers become at individual fibers, the separated fibers are removed from the opening roller. So, it comes out from the opening roller by, so that is a opening roller clothing by air suction. So, here there will be air suction in the transport channel, because the vacuum is created at the rotor groove due to high revolution. So, there is a air suction will be there, the fibers will be sucked from the opening roller and it goes to the transport channel, but the trash particles, heavier trash particle, so that these are ejected. Suction is generated externally to the rotor. The rotor is therefore under the partial vacuum. So, here there will be partial vacuum which will suck the fibers. Now, the separated fibers are further drafted during the transportation in the air flow to the rotor. So, that during this transportation also these drafted fibers are further drafted. Now, here we can see the transport channel shape is the conical shape. So, if this is the conical shaped transport channel here. Now, the velocity at the inlet V inlet and velocity at the outlet are different. So, velocity of outlet is more than velocity of inlet, that is due to the cross sectional difference. The air moves at faster rate in the exit. So, this is important for straightening of fiber. Now, how the straightening takes place here? This is a transport channel. Here suppose one fiber, this is a fiber. So, fiber the tip portion and this is the back portion at the back. The tip portion, the fibers, the speed of air velocity here is higher at the tip, and at the back portion it is at trailing portion it is a lower. So, as fiber is moved by the air stream. So, due to the accelerating motion of air, the fibers get straightened, and at the exit the straightened fiber, almost straightened fibers are landing on the rotor groove. The fibers are individually deposited on the internal wall of the rotor groove. So, that they during the stretching and high drafting, the fibers are individualized, one by one fibers are actually landing on the rotor groove, and then after landing it slides, actually rotor wall first, it is actually internal wall, then the fibers slide into the rotor groove. Okay. And during that sliding also there is a draft, that detail we will discuss later. Here they accumulate in the form of ribbon, fiber ribbon. So, suppose this is the rotor groove. Okay. Here is the rotor groove. So, fibers land here at the wall and then slides inside the rotor groove, and the fiber ribbons, number of fibers are landing. So, they will form fiber ribbons. To initiate the spinning, that means twisting. So, if we want to produce yarn, what we do? We have to feed the yarn, some seed length of yarn is fed, already formed end is fed inside the rotor groove, okay, through the doffing tube. So, that is the initial position. So, to otherwise we will not be able to initiate the yarn formation process. So, when the machine starts, we have to first initiate, we have to first send feed the already formed yarn, and the tail end will enter inside the rotor groove. The partial vacuum in the rotor will automatically suck the tail end, okay, tail end of the yarn onto the rotor. So, there is a partial vacuum inside the rotor groove due to rotor itself, due to the high rotational speed. So, it actually performs two functions. One is it sucks the fibers from the opening roller, and also it sucks the tailing end of the seed length of the fiber yarn. The rotation of the rotor develops air drag and centrifugal force on the yarn. So, the air drag is there in the rotor groove and centrifugal force on the whatever fibers are deposited, okay, and also on the seed yarn length, and pulling the yarn end into contact with collecting fiber ribbon. So, the tail end will start rotating at very high speed. Due to the centrifugal force, it will be reaching to the collecting surface, that is the ribbon within the rotor groove, where the fibers are already collected, and this will be the trailing end will be in contact with the those collected fibers. Simultaneously, the tail end is twisted with each revolution of the rotor. Now, the yarn is being fed, the tail end has reached to the rotor groove, and it will start rotating at the rotor speed. So, for each rotation the tail end will start getting one twist. This twist propagates towards the tail end of the yarn and binds the ribbon onto the tail end. So, the tail end starts rotating, and as it is rotating, so it will bind the ribbon, fiber ribbon which has been accumulated inside the rotor groove. Once the yarn tail enters into the rotor, the delivery of the yarn, delivery roller are set in motion. So, as soon as the tail end enters of seed length enters, we start the delivery, okay, and pulls out whatever yarn is being twisted, whatever fibers are twisted at the rotor groove. So, that will be pulled out. The pulling action on the tail results in peeling of the fiber ribbon from the rotor groove. So, in the rotor, this is the rotor groove, the fibers were laid here and the tail end of the yarn which was rotating, this will start peeling off the fibers. Okay. The degree of twist that is inserted into the tail will propagate, okay, into each length of the ribbon peeled from the groove. So, the whatever at the tail end is given, that the twist is given at the tail end, that will propagate to the peeled length ribbon, okay, thus forming the next length of the yarn. So, it will continue. This process is actually it continues because the conservation of mass flow is there, that is the flow rate of mass are equal, that we will discuss with a separately with example. That means, here at every point in this rotor system, the mass flow per unit time and for every point will be same. That means, per unit time through the opening roller and per unit time even through the at the yarn stage, that mass flow will be exactly same, considering there is no fiber breakage, no loss. So, the sliver feed rate, the build up of the fiber ribbon, okay, to give the required yarn count. And rate at which the ribbon is peeled off from the groove and twist is given to the yarn, and rate at which the formed yarn is pulled from the rotor and wound onto the package. Okay. So, the process will continue. Okay. First sliver is fed, then build up of ribbon, then the ribbon is twisted and peeled off, then yarn is formed. These are the stages. The point at which the ribbon is pulled from the rotor groove is called peel off point. So, here you can see this is the peel off point. So, yarn tail is there and the tail end is twisted because of the rotor rotation, and that this tail end is actually joined with the fiber ribbon, and due to the pull of the yarn, that is yarn tension, as the delivery has started. So, it will start pulling and the fiber ribbon is coming out from the rotor groove. At that point is known as the peel off point, which is denoted as P. Since the ribbon is pulled at the delivery roller speed, so this is pulled at the delivery roller speed V d, the peel off point circulates, okay, the peel off point will move at the delivery speed, okay, V d, and pi dr is the diameter of the rotor, pi dr is the circumference. So that we can calculate the RPM, rotational speed of the peel off point, as V d by pi dr. So, V d by pi dr is the rotational speed of the peel off point. And this means that the every rotation of the peel off point will add one additional twist in addition to the rotor speed. So, peel off point, ultimately peel off point speed will be, peel off point RPM will be rotor RPM, and due to the peeling off, due to the delivery. So, this peel off point P will rotate without any delivery, will rotate at the speed of RPM of the rotor. So, NR is, but when the peel off starts, that is the delivery starts, the peel off point will rotate at additionally at the same direction by the V d by pi dr. So, effective rotation of peel off point will be N r plus V d by pi dr. This is called normal withdrawal, but there is another system which may generate due to the bridging fiber. Sometime peel off point rotates, the rotor rotates in this direction, peel off point we are assuming the rotation in the same direction, but sometime due to the bridging fibers momentarily this continuity breaks and the peel off point starts moving in the opposite direction. In that case, effective peel off point speed will be N r minus V d by pi dr, that we will discuss separately, and this is momentarily, but after that immediately when the bridging fibers effect goes off, again it will start its a normal delivery. This is called, when the peel off point rotates in the opposite direction to that of rotor speed, rotor direction, that is called reverse withdrawal. Okay. NP and NR are the peel off point and rotor rotational speed respectively. Now, this is the yarn tail, as we have seen, and QA is the already formed yarn, and PA is the with the that is the P point is the peel off point, and between P and A the twisting is taking place. To insert the twist into the fiber ribbon to produce the yarn, sufficient twist torque must be present at point P, because this twist torque comes from the yarn twist. Here the already formed yarn, this yarn twist, the tail end is free. So, tail end will actually transmit the torque up to the peel off point. So, this torque must be sufficient, otherwise there will be breakage, discontinuity will be there. So, this torque is actually provided by the yarn tail. This keeps the forming of yarn from actually breaking at point P. Okay. As a result of high tension introduced at the AP zone by the centrifugal force. So, the centrifugal force actually generates high tension, because which tries to push the bobbin ribbon in the rotor groove. So, the high tension has to be there, and so that there should not be any breakage. So, here we need at the point zone AP we need very high twist torque, so that the twisting can take place here. The rotor generates the twist torque as it carries the yarn AP through each revolution. So, that rotor, due to rotor rotation, there will be twisting torque will be there. So, here the QAP acts as a crank. So, this is a, if we see the crank motion, this type of crank motion. So, here this QAP acts as a crank. Okay. The cranking action introduce the twist in QA. So, this is actually introducing twist here QA, and that twist is getting transmitted to the AP zone. The twist torque builds up and propagates towards the P. So, here twist is twisted due to crank action between QA, and this twist torque is propagated towards the P. In doing so, it is to overcome the barrier at A. First A is a barrier of the doffing tube. So, this is the doffing tube. So, this twist torque has to propagate to P. So, first it has to pass the barrier at point A, doffing tube, and causing by the narrowness of the rotor groove. Okay. The spinning tension and doffing tube geometry are therefore important. So, doffing tube geometry has to be perfect, it should be smooth, so that this twist torque can propagate easily. So, overpowering the twist barrier requires high machine twist setting than used in ring frame. So, that is important. Here we have to have high twist in rotor spin. So, that is why in rotor spinning we normally cannot have low twist. So, we have to have high twist. So, if we use low twist, if we want to produce soft rotor yarn, the problem will be there. There will not be any too much the twist torque to be propagated at point P, which may result the immediate breakage. So, that is why we have to have higher twist level than ring spinning. The central area, that is A, which is under the control of the doffing tube, the A termed the doffing tube nozzle. So, here it is a doffing tube, this part, it is a doffing tube exit point, we can tell, can be altered to assist in reducing the twist level required to spin. So, that is why what we have to, we can reduce the twist level, but if we can change the nozzle design. Otherwise, if there is any restriction here at point A, then we have to use a high twisted yarn, we have to produce high twisted yarn for proper propagation. Otherwise, if we can develop a particular novel where there won't be any twist restriction, smooth flow will be there. In that case, we can use the low twisted yarn, we can produce low twisted yarn. Different types of doffing navels are used. The most contrasting effect is to obtain between the smooth and grooved navel. So, these are the different types of doffing tube. Essentially, the grooved navel keeps the false twist effect at. So, not only the smoothness, if there is a smoothness, the proper twist flow will be there. So, it can the twist torque can be propagated up to the P. That was the initial concept, but at the same time, if we use the grooved navel, grooved and smooth navel, grooved navel, what grooved navel will do? Grooved navel will impart false twist at A. That means, false twist at A if we give, so there will be larger twist between P and A and relatively lower amount of twist at Q and A. So, with a lower amount of yarn twist, we can impart more twist or more twisting torque between P and A by using grooved navel. So, that is a false twist is imparted. Thus, if the yarn is being spun in Z twist, say Z1 yarn twist, then the grooved navel will give additional Z twist, say Z2 in the yarn portion. So, there will be Z1 plus Z2 in PA zone, in this zone. So, that this high twist will have sufficient torque, but as soon as it moves out, this Z2 will get nullified, the false twist will get nullified, and effectively the yarn twist will be Z1. So, as this yarn length at this Z1 and Z2 will be there, okay. Subsequently it passes, and therefore, at AQ Z2 will be removed, okay, by S2. So, here it is Z2 false twist, here it will be S2, S direction, Z direction twist in false twist, S direction, that will be actually nullified between A and after A. So, A and Q it is nullified. So, nominal twist is again there in the yarn. So, this is the false twist arrangement, and that false twist effect is prominent when you use the grooved navel. The additional Z2 twist enables the twist propagation, okay. Twist propagation, that is using the higher torque into the small but important part in fiber length, fiber ribbon length with the groove, rotor group. So, within rotor group it actually, although it is a smaller in magnitude, but it helps in the yarn formation and less yarn breakage between P and A. With the use of smooth doffing tube, the twist stops at peel off point. So, that smooth doffing tube if you use, because that will give the slippage here. So, no false twist will be added. So, twist will stop at this point P. Okay. So, at this point, so because of the fluctuation in spinning tension, this is therefore point most likely to break. So, if we cannot transmit twist at this zone within this ribbon, so then there will be a twist breakage at the peak tension. So, this point is, this zone is very weak zone. The grooved dropping tube inserts up to 10 millimeter in the fiber length ribbon beyond the peel off point. So, grooved, so beyond the peel off point we have to see, this is the zone which is important. So, when you use grooved dropping tube with a Z2 additional twist, so the twist is actually inserted up to the approximately 10 millimeter in this zone, okay, beyond the peel off point. So, twist insertion and peel off point do not coincide. So, at this point and peel off point. So, if the twist insertion and peel off point coincide, then there will be breakage, because as soon as the yarn comes, the fiber comes, there is no twist, there is a chance of breakage. So, if it does not coincide, if it is beyond the twist point, okay, so peel off point, then the breakage, chances of breakage will be less. So, there is a twist insertion point beyond the peel off point. So, this is the twist insertion point will be beyond this point, beyond the peel off point. This exerts this extended twist length in the rotor groove is referred as the peripheral twist extent. This is the peripheral twist extent. Okay. Because of the we can use this, increase this peripheral twist extent by either increasing the twist level or by inserting the navel with grooved navel. So, this is the peripheral twist extent. It strengthens the peel off point and enables the spinning at lower machine twist setting. So, if we can reduce the lower twist setting, if we can increase the peripheral twist extent, then the yarn will be formed without any breakage. Now, here you can see the torque stop is there in the zone AQ zone. This is the position. So, in AQ zone we use sometime torque stop. So, if the yarn is positioned, if this is positioned at the contact of yarn length AQ in this zone, the torque stop, then the twist flow along AQ will be restricted. So, whatever twist is there, the problem is that the whatever twist is imparted between AP zone, that gets, most of them are gets transmitted to the AQ zone. That is why the twist get distributed and we are not able to get the peripheral twist extent here. So, when we use this torque stop, that means whatever the yarn produced, that will be actually, the yarn will be there, but the twist flow from this AP zone, the twisting zone will be restricted, okay, towards the AQ zone, causing a build up of twist at A and thereby in AP. So, here the torque stop is as a development where we can increase the twist level between P and A. even though above development improves the twist flow along the yarn tail AP, the minimum 100 fibers in the yarn cross section is required, okay, for efficiently spinning. 100 fibers are required minimum. We cannot reduce the number of fibers like the ring spinning. This gives physically limitation of fineness of count. So, here we need certain torque to flow. So, torque, the twist is there, but we need, if we reduce the number of fibers, then what happen? The torque, twist torque will not flow from A to P, and then immediately breakage will be there. So, we need minimum number of fibers, that is the limitation of the rotor spinning. So, we cannot produce finer count here, except for very short fiber like comber waist, or that is a different type of blend, okay, which would have to be spun in coarser yarn. Minimum figure almost depend on the fiber length. So, if we use the fiber length, longer fiber, then we can try to reduce little bit without any breakage, but longer fiber length we cannot use in the rotor spinning, because of the, it will produce higher number of bridging fiber, that will create problem during the spinning. For ring spinning, because of twist usually flow radially, so there we can have minimum number of fibers. So, 40 to 90 fibers, okay, depending on the length, strength and twist. So, that is why in ring spinning we can produce finer yarn from the same fiber linear density. So, long staple fiber. So, in the long staple fiber we can have the further lower number of fibers. Therefore, for a given fineness, fiber fineness, the longer the fiber, the smaller the minimum number of fibers required in the yarn cross section in the ring spinning. But this is not true for the rotor spinning, because rotor spinning we cannot use the longer fiber. Okay. Now, we will stop here. In the next session we will discuss the rotor yarn formation, okay, by cyclic aggregation. And what is cyclic aggregation? That is the fibers are landing one by one. So, that will form a in the cyclic form as the rotor is rotating and peeling is taking place. So, all these things issues we will discuss in the next session. Till then, thank you.